All right, going on to the next problems. Next, after we did the inequality theorem, you need to be able to do the triangle exterior angles theorem. So I'm going to start you off. I'm just going to do kind of a little bit more challenging one. There will be an easier one on the test. There's two of these. There will be one just with kind of some numbers just to show that you know the theorem. But we're going to do one that involves a little bit of algebraic work. So I've got one here that's 2x plus 20. I know this angle here is x plus 30. And I know that this angle down here is 2x plus 70. So the exterior angles theorem says that if you take an exterior angle, which in our case is 2x plus 20, it will always equal the sum of the two remote interior angles, or the two angles that are not touching the exterior angle. So we're going to sum these together. X plus 30 plus 2x plus 70. So my x plus 2x gives me 3x. My 30 plus 70 gives me 100. Once you sum these two angles together, you're going to set it equal to 2x plus 20. I see a lot of people jumping in with 180. Remember, 180 is only if you know all three interior angles. So I've got 3x plus 100 equals 2x plus 20, which came from the exterior angle. So we're going to solve this. So looks to me like 2x is smaller, so I'm going to subtract 2x from both sides. Those will cancel. Here, 3x minus 2x is going to give us 1x. Bring down my positive 100. Bring down my equal sign. My 2x is canceled, so I'll just bring down the 20. And all I need to do now is subtract 100. And this is going to give me a really stupid answer, probably because I just made it up. But we're just going to go with it. So my hundreds cancel, so the x comes down. 20 minus 100 is negative 80. And I know that's not going to make sense because when I plug it back in, I'm going to get negative angles. But it's still the exact same process, so disregard the fact that it's completely not a real possibility, because when I plug negative 80 plus 30 is negative 50, and we can't have an angle that's negative 50 degrees. That's silly. All right, next we have triangle proof questions. And I told you guys there's going to be two, but I'm only asking you to do one proof. The first one is based solely off of, can you identify the triangle congruence theorems if I give them to you? So you should recognize that ASA is a theorem. SSS is a theorem. SAS is a theorem. AAS is a theorem. And HL is a theorem. Those five. Side, side, side. Easy. Triangle got SAS. And then just do the opposite. Triangle's got ASA. And the only weird one is AAS, which, remember, that looks kind of similar to the bad word theorem that is not a theorem. Quick hint, geometry teachers, we don't do funny things. I told you that a while ago. I am not going to write ASS on your test. If you're looking for one that doesn't exist, I'll probably write SSA. That way I'm not writing a bad word on your test. This is not a real theorem. Remember that. If you read it backwards and it's a bad word, that is not it. So an example of one that you might be having to actually prove might be given triangle A, B, C, and triangle BCD. And I'm going to say that you're given that, hold on, let me draw a picture over here. So I've got A, B, C, D, C, B. Great. I'm going to say that in my given, AC is parallel to BD, and I'm going to also say that angle BAC is congruent to angle BDC. So I've given you quite a few pieces of given there. Well, I mean, I said this up here in given. It's not really important to us. So I want you to prove that triangle ABC is congruent to triangle BCD. Actually, scratch that. We're going to take a little bit step further. We're going to prove, I want to prove that segment AC is congruent to segment CD, or DC. DC, to make it in the correct order. AC, DC. Ha, it's a band. All right, so let's do that proof. So I'm going to drop my two columns here. I'm going to put my S over here and my R over here for statements and reasons. Statements start off first. First thing, AC has to be parallel to BD, and that was given. So in my picture, to make sure that we get this, let's go up here and make AC parallel to BD with those little arrows. Now, hint for myself, I see parallel. I need to start thinking alternate interior angle. So I'm going to make a little note over to myself. You can't see my little note. I made a little note to myself over here. This is alternate interior angles because I know I'm going to need it. I know that that's what that has to do with. And then my other given was that angle BAC is congruent to angle BDC. And again, given. And we want to mark that in our picture. BAC right here is congruent to BDC right here. So if I were to look at that picture, I recognize, hey, there's going to be a hidden side here from the reflexive property. Cool. And I recognize, oh yeah, there's something going on with those alternate interior angles. So I know that I'm probably going to have to use something with two A's and an S, which is either going to be angle side angle or angle angle side. So got to start thinking that way. So let's first mark the quick one. I know that BC is congruent to BC right here from the reflexive property. It's a hidden side. They share that side, so I need to think reflexive. And then this one, it's the tricky one. If I said something was parallel, well, these are my two parallel lines, right? And here's the line that makes them zigzag. So if I look at that zigzag, what are the angles that have to be congruent? Well, ACB has to be congruent to DBC. So angle ACB is congruent to angle DBC, and we can say alternate interior angles and theorem. Oh, there you go. All right, so I have an angle here. I have an angle here, and I have a side. I think that's enough to prove congruence. Angle, angle, side. A, S. Angle, angle, side. Angle, angle, side. So we can now say that the line, this step here, triangle ABC is congruent to triangle BCD. Remember, I threw a little trick here, though. I said we didn't want to prove that. I wanted to actually prove that AC is congruent to DC. And we didn't do a lot with this. But if I just proved that these triangles are congruent, doesn't that mean CD and AB have to be equal to each other? And it does, because they are corresponding parts on two different congruent triangles. So we used a theorem called corresponding parts of congruent triangles are congruent. CP, Anytime it tells you to do an extra step after that triangle proof, that's probably what you need. All right, we're getting closer. So next after that, we had special segments of triangles, and I brought a little chart to help us because I posted another video to help you out with doing these and recognizing these. So let's just look at this one. I kind of jumbled them up and scribbled them up a little bit. So starting off, we want to find, we're given the definition that a point of concurrency is equidistant from each side of the triangle. I remember that because if it's from each side of a triangle, let's draw a diagram. So there's a point, and it's equidistant from the sides. That means that inside this, we can fit a perfect circle called an incircle. And if there's an incircle, we know our point of concurrency is an incenter. And think, Pamasico, what goes with I? Well, there was an A in front of it. So this was an angle bisector. And we could draw an angle bisector here. Boop, boop. Boop, 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 boop. And here, 1, 2, 3, 1, 2, 3. That's a terrible drawing, but this is what you should have had right here. Notice all the angles are marked. Mine is just with a marker, so it's hard to see. And next, they told me this is a median, and the point of concurrency is created by a vertex connected to a midpoint. What kind of point of concurrency do they have? Medians. Remember, median meant middle. Centroid sounds like center, so centroid and middle mean very similar things. And if we were to draw this, I'll try and draw this one better. We start at a vertex and we go to the midpoint of the other side, separating it into two equal pieces. Start here and go to the other side, separating into two equal pieces. And start at the vertex and go to the other side, separating into two equal pieces marked with a 3. Next, the point of concurrency is equidistant from the vertex of the triangle. Remember, we said that that was the other bisector. It was the one that made a circle go around the triangle because it touches all the vertexes. And that was perpendicular bisector. And perpendicular bisectors also P goes with C in Pamasico, P and C. So we said this was a circumcenter. And if I wanted to draw this one, there's my triangle, we would go to the center of each side and draw a line coming straight up so that it makes 90 degrees and splits these. It has a lot going on. Over here, go to the center, make a 90 degree, and it splits these evenly. Over here, go to the center, make a 90 degree, and split these evenly. That's scary because I drew too much there. But it would look like this one. See, there's a box. You can't really see these markings because they're really light, but there's markings here, there's markings here, there's boxes here, boxes here. That's what you're looking for. My last one is altitude. And altitudes we knew went, oh, that should go over there. Altitude is a segment. The segment has an orthocenter. And again, if you're looking at this one you should see from each vertex drops down to make a 90-degree angle. Nothing other than 90s. That's all you should see here. Just 90s. No sides marked. Just 90s. Beautiful. Look over that worksheet we did on Tuesday. That one really is beneficial to this. All right. That leaves me with 2 more topics. Moving back to my own notes. The second to last thing we're going to do is a mid-segment question. Mid-segment. So there will be one question on mid-segment. And mid-segment was pretty simple. The mid-segment just was if you connect all of the midpoints inside a triangle to make another little triangle, that triangle will be exactly half the perimeter of the big triangle. Or if I told you that AC and DB, we'll just put the letter E up here just to have it. But if I told you that AC is equal to 4x plus 8, and I told you that DB is equal to 3x plus 2. Well, we said there was a special relationship. We said that AC is exactly twice as big as DB, or that this piece, and this piece were all the same. But there's 2 of those down here, so it's 2 times bigger. Well, I can solve this for x then. That's what I want you to be able to do on the test is solve for x. Because I look here and I say, well, DB is right here. Well, if I take DB and I multiply it by 2 because it's small, it will become the same thing as AC, which we know AC is equal to 4x plus 8. So I'll just distribute this 2. We get 6x plus 4 equals 4x plus 8. And we'll solve this now. Subtract 4x because it's smaller, so I'll subtract 4x from both sides. 6x minus 4x is 2x. Bring down the 4. 4x minus 4x cancels, so I'll just bring down the 8 to keep my equal sign. And we'll subtract 4 from both sides. Ooh, this is going to be pretty. I didn't expect it to. Bring down the 2x. 4 and negative 4 cancel. 8 minus 4 is 4. And just one last step, divide by 2. X equals 2. There you go. That's a mid-segment question. One last question. Well, it's 3 last questions, but it goes hand in hand. I'm just going to do this side here. So this is the centroid theorem. And it says that there is always a short and a long side in a centroid. The short side, you can see here, GF, is always half the length of the long side. Look here in JGE. GE is the short side, so it will be half the length of JG. Same thing here, DG will be half as big as GL. So if they tell you here that GF is equal to 15, well, I look here and I see GF is this piece right here. It's pretty short. They want me to find KG, which is the long one. So if this is short, to turn the short one into the long one, we have to multiply it by 2. So 15 times 2 gives me 30. Here they told me JG equals 13. Well, JG is a long side. They want me to find, JE. They want me to find the whole thing. So if JG is 13, well, then we can take half of JG, so divide by 2, and we get 6.5. And since we want J to E, the whole thing, we can just add those 2 numbers together. 13 plus 6.5 is going to give us 19.5. So the whole thing has to be 19.5. Number 3 tells me JL, the entire base here, is 22. Find FL. Well, we said that since these are medians, it's coming down and intersecting this to separate it into 2 equal pieces. So if the whole thing's 22, then what does each one have to be to make it fit? Well, they each got to be 11. Probably won't have anything like that. More towards the top is more important for us right now. Same thing there. We're going to skip over that one too. Let's just go down here. This one says, hey, DL is 24. We did this one in class. Let's do this one instead. Does that one work? It doesn't work. Let's do a different one. We did that one in class. Let's do this one, number 9 over here. This one says OE is equal to 22. So find EP and OP. So if we look here, OE is 22 units. So I want to figure out what each of these pieces are. So remember we said that if you've been given the entire line, the entire special segment, we just divide by 3. So 22 divided by 3 is going to give me 7.33. 3's repeat. So I know this short segment is 7.33. And if I want to get the big segment, I just got to multiply that number by 2. And I get 14. We're going to round it up to 0.67. So the little one is 7.33. The big one is 14.67. And you can add those together and double check that they reach 22, and they will. So divide by 3 gets you the small one. Multiply the small one by the big 2, and you'll get the big one. So up here, EP was 14.67. And OP was 7.33, repeating. And if you can do all that, you are set for this test, and you're going to be golden. So make sure you look over that stuff, watch this video again if it will help you, and good luck studying.